pleasure to be speaking here. It's very funny to hear someone introduce me as doctor, because I got my degree like 2 months ago, so it feels good. So I'm going to talk about chip firing today, which is a very simple game that you can play on graphs. It has connections to various areas of mathematics and really the sciences at large. Sort of my goal today is to talk about a new perspective on what chip firing is. And in particular, I want to talk about this in the context of Riemann-Roch theory for graphs. So Riemann-Roch formula for Riemann surfaces, or for more generally for algebraic curves, is a rather famous theorem from algebraic geometry. It's one of the cornerstones of modern algebraic geometry. And there is a graphical version of this due to Baker and Noreen. It's all based upon chip firing. So you use chip firing to prove a Riemann-Roch theorem for graphs, and I'd like to talk about how to understand that in the language of orientations. So just we'll start at the beginning with what is chip firing. So we have start with some graph. So say K4 minus an edge, and label the vertices. Now when I say chip here, I mean chip as in a poker chip. So if you're used to the card game poker, you play with chips, not computer chips, okay? Just poker chips. So we'll imagine a certain number of chips sitting at the vertices of the graph, which are indistinguishable. So a really simple setup would be we have zeros at these three guys, and there's 2 chips sitting there. Now the basic operation is firing, whereby this vertex will fire and send 1 chip to each of his neighbors and lose that many in the process. So if we say V0 fires, then we get a new configuration which looks like this. Okay, so is it clear? Previously V0 had 2 chips. He fired, he sent 1 chip to V3, 1 chip to V1, and lost 2 chips in the process. Okay, so that's the basic setup. So this is really essentially a combinatorial language for understanding the translates of the Laplacian lattice. So this is the lattice which is generated by the columns of the Laplacian matrix. So I'm not going to harp on this for too long, but if you know what the Laplacian matrix is, I'll just write it down just to recall. So the diagonal is going to be the degrees. So we'll have 2, 3, 2, 3. And then we'll have the off-diagonal entries are the adjacency matrix. So the adjacency matrix is going to be -1s everywhere, except V0 and V2 do not share an edge. So that means we're going to have a 0 here, and then everywhere else. Is that correct? Yeah, there we go. So this is the Laplacian matrix. The degree on the diagonal and the off-diagonal entries are coming from the negative of the number of edges between a pair of vertices. So this is, say, Q. And we can describe this configuration of chips as a vector. And so if we have this vector, it's going to be 2, 0, 0, 0. And if we subtract, so this E1 is the characteristic vector, which has 1 in the first entry and zeros in the other entries. So what I'm saying is if we subtract the first column from this vector, this precisely corresponds to chip firing. And you see that the new vector you get is 0, 1, 0, 1. Okay? So all I'm trying to say is that this operation of subtracting the first column precisely corresponds to chip firing. So that's essentially why it's such a fundamental concept. So it was discovered in different communities independently around the same time in statistical physics by Bach-Tung and Weissenfeld. So
do you have a reverse operation as well?
Yeah, so this is the basic setup, but then there are slight variations on this that one might care about. So generally you won't have an inverse operation, you just have this setup, and you also insist that the number of chips is non-negative. In my setup, things are going to be more free. So you are going to allow negative numbers of chips and inverse operations. So you call that a borrowing instead of a firing. So that's also okay. Yeah, so maybe since I don't want to spend too much time, I just will mention in passing, this was discovered in statistical physics, also in graph theory by Björner, Lovaas, and Shor. And actually, originally, I guess, is due to someone from discrete probability who realized that you could use this setup as a way of teaching elementary school students about Markov chains. So this is a rather unorthodox approach to trying to teach probability to little kids. You can use this to, in a certain way, to calculate the limiting distribution for a Markov chain. So and that was due to Engels. And then actually independently, around the same time in the early 70s, this was basically also due to a guy named Mazessian who was investigating posets. And that's sort of, he was looking at acyclic orientations, which are just a Hasse diagram for a poset, if you know what that is. More generally, you can look at acyclic orientations of graphs. And he noticed a certain relationship between chip firing and acyclic orientations. And that's sort of what I want to expand upon today. Okay, so now I'm going to draw another picture. Sorry to make everybody stare at this side of the wall the whole time, but so this is the most important picture today. Maybe I should use a different color. Or can people see blue on green? I think red is better. Okay, so now I want to, for the rest of the talk, I'm going to be talking about a different game, which I call the Generalized Cycle-cocycle reversal system. It's a bit of a mouthful, but I'm just trying to be consistent with previous terminology. So this is the Generalized Cycle-cocycle reversal system. Okay, so there are three different moves. Okay, what's our input? Our input is a graph, which will be fixed. Okay, same as with chip firing, we're working with a fixed graph. And we're going to be working with partial orientations of this graph. So by a partial orientation, I mean that for every edge, you have three choices. It's either oriented in one direction, the other direction, or like this edge, it's just unoriented. So those are your three choices. So that's your input, a fixed graph, and a partial orientation, but the partial orientation is going to evolve over time by these three different moves. Okay, so the first move is an edge pivot. So this is if you have an edge which is oriented towards a vertex, and this vertex is also incident to an unoriented edge, then we can swap the orientations, right? So we unorient this edge, and then we orient this edge towards V. So the reason I call it a pivot, if you know this word pivot, it means to rotate something with one end fixed, right? So we're just pivoting this edge orientation.
Can you do that if that vertex has many other edges?
Yeah, that's fine if it has other edges. It's just important that we pivot it to an unoriented edge. So this vertex is incident to one edge pointing towards it, and another one which is unoriented. Yeah, please ask questions because this is like the basic idea.
So it's swapping an oriented edge and an unoriented edge.
Yeah.
No orientation on the edge.
Yes. And it's important that this edge is oriented towards the vertex we're pivoting it at.
Okay.
Yeah. So if it was oriented the other way, we couldn't do that.
Sure.
Okay, so the second move is a cut reversal. So if you have a cut in the graph, if you partition the vertices into two sets, and you look at the edges going between them, that's a cut. And if the cut is consistently oriented, so all of the edges are pointing in one direction, like in this picture, they're all pointing upwards, we can just flip all of the edges in that cut and make them point downwards. So that's the second type of move. And then the third type of move is a cycle reversal. So cycle reversal, similarly, if you have a directed cycle, so you have some cycle in the graph where all of the edges are pointing in the same direction, then you can reverse the orientation of all of the edges in that cycle.
Could you explain the cut reversal again?
Yeah, so the cut reversal, so a cut in the graph is just the set of edges going between two, like a partition of the vertices.
Okay, yeah.
Partition the vertices into two sets, look at the edges going between them. So those edges cut the graph, that's why you call it a cut. And I'm saying if all of the edges are oriented in the same direction, then you can reverse that.
In one partition.
I'm saying like, so we have these three vertices on this side, and we have these three vertices on this side, and these are the four edges going between them, and they're all oriented upwards.
So every edge has to be oriented.
Every edge has to be oriented. So for both of these moves,
I see.
same direction, absolutely, yeah. So it's not an algebraic thing, it's a combinatorial thing.
It's the same orientation between the two partitions of the vertices.
I'm saying you have an induced like direction in the sense that there's this side of the cut and there's this side of the cut. And I'm saying every edge should be oriented in the same direction.
Right, so I couldn't cut the bottom vertex from the 5 top ones here.
The bottom vertex.
I couldn't make.
Yes, exactly. So if you took this vertex and you looked at the rest of it, that's not a consistently oriented cut.
So in this graph, you don't have any other example for cutting. You can only cut there.
This is
So there's another one.
this is possible.
Is there another one? You see one?
The top one.
Yes, that's right. So if we cut along here, that's correct. So that's if we take these two vertices and then we have everything else, then these three edges are oriented in the same direction.
Okay. Then do it.
So that one's also okay. Yeah. Okay, so let me just say a few words about the history of this game that I've introduced. So the first person to think about anything like this, as far as I know, was Mazessian. And so Mazessian was responsible for acyclic full orientations. So I shouldn't write it here. I'll move back over to the other board now. Okay. So Mazessian considered acyclic full orientations. So what do I mean by that? I mean that there are no unoriented edges. So every edge in the graph is oriented, and there are no directed cycles. So that would be what Mazessian was thinking about. And in that case, he wasn't thinking about anything quite so. So in that case, we don't have cycle reversals. We also don't have edge pivots. So the only thing we have are cut reversals. And in his case, he actually noticed you don't have to look at cut reversals. You can only look at what he called sync reversals. So where you pick a vertex where all of the edges are pointing in to that vertex, and you reverse the orientation. So for example, suppose we have our ongoing example. Let me give a full acyclic orientation of K4 minus an edge. Okay? So now I've oriented every edge, and there are no directed cycles. So it's a classic fact that every acyclic full orientation has some sync. So in particular, this guy is a sync. So now what we can do is reverse the orientation of all of the edges pointing towards that sink. So he called this a sink reversal. Or, well, at least that's what other people call it. His paper's in Russian, which I can't read, so I'm getting this secondhand from a person named Pretzel, who I guess can read Russian. Okay, and so he studied this game. He was actually looking, like I said, at Hasse diagrams for posets. He noticed that this operation turns one Hasse diagram for a poset into a Hasse diagram for a different poset. So that's what he was thinking about. So anyway, in this game, somehow you don't actually need to think about cut reversals. It's sufficient to just think about sink reversals. Okay, so I sort of just
think about source reversals.
One could, but in his game you don't. You just work with sink reversals. For him, it was a maximal element in the poset, and he called it a pushing down. So you take a maximal element in your poset and you push it down a level. So okay, I've talked about these two different games: chip firing, generalized cycle-cocycle reversal system. What's the relationship between the two of them? Okay, so let's look at the in degrees -1. So don't worry too much about this -1 for now. But for every vertex, we want to count the number of inward pointing edges. -1. So hopefully you can see this in the back. Okay, so this vertex has 2 incoming edges. So 2 minus 1 is 1. This vertex has 2 incoming, -1 is 1. This vertex has 1 incoming edge, -1 is 0. And this vertex has 0 incoming edges, -1 is -1. Okay, if I do the same thing over here, I get -1, 1, 2, -1. Okay, so can anyone see what the relationship is between these two counts?
It's like a tick fires from the upper.
Yes, exactly. So the relationship between these two lists of integers at the vertices is precisely that we've fired the vertex at the top. Okay?
Yeah,
and if you,
that's even without -1. Right? I mean, even if you don't have a -1.
yeah, exactly. So the -1, this is important for what I'm going to do, so I'm introducing it now. But you're right, the -1 is not important for this observation. And yeah. So don't worry about the -1. Just notice how things change. And it's rather intuitive, right? I mean, you just look at it, that's exactly what's happening. He's losing his degree number of edges pointing inwards, and each of his neighbors is gaining one more edge pointing towards them. So that's precisely chip firing. Okay, so this was Misesian in like the early 1970s, and this surprisingly was not generalized to arbitrary graphs until 2007. And so then in 2007, Jiwan looked at arbitrary full orientations. So what I mean by that is that now we still don't have any unoriented edges. We don't have this, but we do have possibly cycles. So Jiwan said, okay, well, let's look at more generally than sink reversals, let's look at cut reversals, and let's look at cycle reversals. So he introduced okay, and he called this the set of all full orientations modulo these two operations. He called this the cycle-cocycle reversal system. So, and that's why I use this terminology to try to be consistent with him, even though I don't necessarily think it's the best. But Okay, so what was he interested in? Well, he's kind of an oriented matroids sort of person. And so he's very interested in the Tup polynomial. And what he was able to get with this setup was he said, okay, using this, there are a couple of things you can do. First of all, if you look at the set of all orientations, okay, modulo cycle-cocycle flips. I'm being very informal now, so this is just orientations, modulo cut flips and cycle flips. The size of this set equals the number of spanning trees. This is a rather beautiful result. And he actually got something quite a bit stronger. He said he actually gave a unified interpretation of all of the evaluations of the Tup polynomial for integers between 0 and 2. So if you know anything about the Tup polynomial, this is the Tup polynomial evaluated at 1, 1. And he actually got a unified interpretation of, say, t of xy so for all integers x and y between 0 and 2. So then, I guess maybe the very next year, or I think it was next year, maybe 2 years later. So Olivier Bernardi, in his PhD thesis, he actually gave a bijective proof of all of these enumerations. So then Bernardi gave a he gave this bijective proof. In particular, he gave what he called a master bijection. And when you specialize this bijection, you recovered all of these different enumerations. And he used using ribbon graphs. Okay. How am I doing? That took 25 minutes. Do we go till 5 or do we go till 10 to 5? 5? Okay, well, I don't know.
Of course.
Okay.
Of course, 5.
Great. Okay. Good.
I need to know what ribbon graphs are.
No, it's just for specialists maybe. What it is you fix a cyclic order of the edges around each vertex. And so what this essentially does is it gives you a combinatorial embedding of your graph into a surface, into an orientable surface. So the reason why you say ribbon is you imagine a thickening of the edges so that it becomes like a ribbon, and you embed it into a surface. Okay. And Bernardi has gone on to use this idea about ribbon graphs relating to the Tup polynomial in a lot of different ways. Okay, so that's maybe enough about history. I just want to give some motivation for this setup. So now my main contribution is to try to study partial orientations and say, okay, well, we certainly need at least this one extra move. Okay, if we want to be able to describe a nice relationship of partial orientations which somehow encapsulates chip firing, then we do need at least this extra move. And so my main theorem maybe is that this one extra move is sufficient. Okay, so I'm going to call, so if you have a chip configuration, say D and D prime, we'll write D tilde D prime for saying you can get from one to the other by chip firing moves. And if we have two partial orientations, say O and O prime, I'll say you can get from O to O prime by these three moves, and you have this other equivalence relation. Okay, and then the last thing I should also say here is that, okay, just to set up the notation, if this is an orientation O, I'll refer to the associated chip configuration as D sub O. Okay, so we start with partial orientation, just look at in degree minus 1, that's an associated chip configuration. So the first theorem.
So here you assume that you also use borrowing operation as well?
No.
When you write equivalence.
Oh, I see. Yeah, maybe I should, yeah. Yeah, so it's not necessary, but yes. Okay, let's agree that you can also do that. Okay. Okay. So the theorem is that two partial orientations are equivalent in the generalized cycle-cocycle reversal system if and only if the associated chip configurations are equivalent in the chip firing game. Okay, let me say a little bit about why one direction is obvious. So I claim, first of all, that if you have two orientations which are equivalent by these three moves, then the associated chip configurations are definitely chip firing equivalent. So why is that obvious? Well, what happens to the in-degree sequences at the vertices when you do an edge pivot? Stays the same.
Yeah.
Nothing happens, right? I mean, certainly nothing happens to the rest of these vertices, and for this one vertex where we've done this local operation, the in-degrees stay the same. Okay, so nothing happens. And the same thing is true for the cycle reversal. So if you do a cycle reversal, when you change this, every vertex has the same number of incoming edges. So that stays the same. So then the one that's really interesting is this cut reversal. So what happens when you do a cut reversal for the associated chip configuration? Well, I claim it's precisely firing all of the vertices on one side of this cut. So why is that? So think about locally, if we have, so suppose I'm drawing a picture of a cut. So we have some of the vertices on one side, the other vertices on the other side of the cut. If we fire all of the vertices on one side, we'll look at each edge that's contained in this side. So one vertex on one side is sending a chip in this direction, and the vertex on the other side is sending a chip in the other direction. So it just cancels out. And that's true for every edge that's contained in this side of the cut. So internally, everything cancels out, and all you need to do is look at the boundary of this cut to understand what's happening. And in particular, each vertex on the boundary just sends one chip across the cut along each of its edges. So that's precisely, in the same way that we understood the sync reversal, that's what's going on with the cut reversal. So if we fire all of these guys, then that's precisely everybody on the boundary sending one chip along each of its outgoing edges. Okay. So that shows that one direction is obvious. If you have two orientations which are related by these two moves, then they're certainly chip firing equivalent, or excuse me, their associated chip configurations are chip firing equivalent. So the interesting part of this theorem is the converse, and that's what takes some work, is to prove that if you have two, you start with two orientations, you assume that their associated chip configurations are equivalent by these chip firing moves, and then you have to reverse engineer a bunch of moves like this to get from one to the other. So that's the idea.
Can I ask something?
Yeah.
Your graphs are, without the orientation, the underlying graphs, these are simple graphs?
So they can be multigraphs, but no loops. So meaning you can have multiple edges between a pair of vertices, but I insist that there are no loops.
But if you have a full orientation of a graph where you allow multiple edges,
Yes.
doesn't it kind of model this situation where you have these unoriented edges? If you have a pair of edges, one going each way, right? Between two vertices, you have an edge going this way and an edge going this way.
But I'm also,
Kind of model this situation.
no, because I'm also allowing the possibility that both edges are oriented in the same direction.
Yes. then you wouldn't have this unoriented. I'm just thinking if I replace where I have these unoriented edges, I just replace by two edges going in opposite directions. And then I work within the
No, because I'm saying
oriented graphs with multiple edges. Does it become the same game, or is this?
I see what you're saying. Yeah, no. That's a very good observation.
Because it seems like the edge pivot still would be the same.
Yeah, I want to say you're right, but
Or maybe it's not.
but you have to be very careful.
Yes.
There's a very subtle thing going on in the background. Yeah. So it's a very interesting question. I believe the answer is yes, but I haven't checked all the details.
Okay.
Yeah. Because I mean, what's wrong? Okay. Well, how should I say this? I mean, the way you've stated it, no. The answer is no.
Right.
But there should be a fix.
Yeah.
Yeah.
Okay.
Okay. Any other questions? Okay. So where was I? Okay. Yeah. So now I guess sort of the intuition now about why this is an interesting result is that now you can see this chip firing game as being a sort of a shadow of this game that we're playing with orientations. And somehow in this way we have more information encoded in this game about partial orientations than we do by just looking at chip firing. And so I'm coming from this community where sort of tropical geometry community, and I don't want to get too much into explaining the connections there, but like I said, there is this Riemann-Roch theorem for graphs, and what I'd like to do in the remaining half hour is to try to explain the statement of the Riemann-Roch theorem and say a little bit about how this this lends itself to a more conceptual proof of the Riemann-Roch theorem. Okay. Oh yeah, one other combinatorial thing that I wanted to mention, like the other important ingredient in proving this statement, is something which I call a Jacob's ladder cascade. So I'm very curious to hear what the name of this game is in Korean. I mean, I'm assuming that there is such a game, but okay, so okay, so the idea is that if you have a directed path, this is sitting somewhere inside of your partial orientation. If you have a directed path from one vertex to another, and the terminal vertex is incident to an unoriented edge, then you can perform this sequence of edge pivots to free up the initial edge and to orient all of the other guys in the opposite direction. Okay? So all I'm doing here is a sequence of three edge pivots in a row. Okay? But this winds up being somehow the most important combinatorial technique in the paper. You use this over and over again, basically, to prove things. So we have, I don't know, when I was a kid, there's this game where you have like a ladder and you flip it like this and the things flop back and forth. Have you seen that? We call this a Jacob's ladder. So I don't know if there's a name for this in Korea. I don't know. Okay. Anyway, yeah. So that's the one other combinatorial thing I wanted to say about how to prove this result. So sort of one way of intuiting why this is important is that this edge pivot is a totally local operation. And when you use these successive edge pivots, it becomes less of a local thing. Okay, so now I want to be more precise about what type of chip firing model I'm thinking about. So, okay, so Baker and Noreen asked the following question. Okay, so given your graph and some chip configuration, which is allowed to have negative numbers of chips, right? So in what we were looking at in this example here, everything is non-negative. But suppose we're allowed to have some vertices having negative numbers of chips. So when is it possible, so I'm saying when is D equivalent to some non-negative chip configuration by chip firing moves? But saying when is it possible by chip firing moves to bring everyone out of debt? Okay, so it's a fairly natural question. So if you phrase this in the language, okay, so this is sort of the first question that's leading towards drawing analogies between classical divisor theory for Riemann surfaces and chip firing on graphs. So I'm going to just, for those who know a little bit about Riemann surfaces, the correct statement here for a Riemann surface would be saying, given a divisor, when is your divisor linearly equivalent to an effective divisor? Okay. So here, a divisor, in their terminology, a divisor equals a chip configuration. Okay. Just want to make this point somehow. Okay. Because I always say divisor, not chip configuration. I'll probably just say divisor from here on out. Whenever I say divisor, you hear chip configuration. So they gave an algorithmic solution to this problem. And it involved certain things called reduced divisors, which are sort of rediscovered in different chip firing scenarios. And it gives you, like I said, it gives an algorithmic solution to this problem. And this algorithm actually leads towards a proof of the Riemann-Roch theorem. So here is sort of my answer to this question. Okay, so my answer would be okay, one of two things is true. So sorry, I realize I'm about to okay, let me introduce some more terminology now before I go any further. So if I refer to the degree of a divisor, this just means the number of chips. Okay? And also I want to say the genus of the graph is the number of edges minus the number of vertices plus 1. So you can think of this as an Euler characteristic, or equivalently this is the dimension of the cycle space of the graph. Okay, so here's my answer to their question. Okay, so given some divisor, with at most degree minus 1, excuse me, with at most g minus 1 chips, then one of the two following things can occur. Can you guys see this in the back? Yeah, okay. So one option is that D is equivalent to some divisor associated to an orientation where O is sourceless, Or, and I'll say what sourceless means in a second. D is equivalent to some D prime, which is dominated pointwise by some D sub O. Where D sub O, where O is acyclic. Okay, so let's talk about the first option. So D should be chip firing equivalent to some divisor which is coming from a partial orientation where O is sourceless. So notice what can we say about the divisor associated to a sourceless partial orientation? Okay, so the basic question is if you have a sourceless partial orientation, meaning that every vertex has at least one incoming edge, then what can you say about the associated chip configuration or divisor? So remember, the map is just in degree minus 1. So if it's sourceless, that means every vertex has at least one incoming edge. So that means that's precisely saying that this divisor is non-negative. Okay. So this, if we're in case 1, this means there is a way of winning the game. Okay, and then, so then the second case is saying, because these are mutually exclusive, it's saying that you can't win this game. But the only reason why that is so is just because it's not the first case. Since it's not the first case and it's the second case, and they're mutually exclusive, it means that if you are in the second case, then you can't win the game. So somehow being the divisor coming from an acyclic partial orientation is like saying you can't win this game. So this is the first sign that acyclicity is something very fundamental here. Okay, so therefore, if O is acyclic, then the associated divisor is not equivalent to a non-negative configuration. So there's something else which is wrapped up in this statement. I kind of have tried to put two theorems together into one to save time. But notice that not every chip configuration is coming from a partial orientation. Right? I mean, there's only a finite number of partial orientations, but these divisors, they're coming from everything which is integer valued. So you want to be able to find, if we're going to be able to talk about questions about more general objects like this, we have to have a way of reducing our questions to questions about partial orientations. And that's what this statement also does.
What's the exact definition of acyclic graphs? When you have unoriented edges,
So there's just no directed cycles.
So
you cannot use the unoriented edge. You can only use directed edges as parts of cycles. Thanks. Yeah, so for example, like this is an acyclic graph, even though you could fill these edges in to make a cycle. Okay. So, of course, I'm taking more time than I thought I would, so let me sort of move along and try to state more theorems, and then I'll stop. So, okay, so there's a refinement of this question. So suppose that you are equivalent to some non-negative configuration. You might then ask, how many chips do you need to subtract so that you can't win anymore? So suppose you can win, how many chips do you need to remove cleverly so that you can't win anymore? So they introduced this quantity, they called it the rank of a divisor. Oops, sorry, I'm getting ahead of myself. Then okay. So this is sort of their fundamental quantity they associated to a chip firing configuration, chip configuration, and this is what the Riemann-Roch formula describes, is this rank function. And it's a certain symmetry statement about this rank function. Okay, so there's one more thing I think I need to define before I can write down the Riemann-Roch formula. Okay, so there's a distinguished chip configuration or divisor which is called the canonical divisor. And this just means that you put degree of V minus 2 chips at each vertex. So for example, for this ongoing guy, the canonical divisor is going to be 0, 1, 1, 0, which is exactly what I have up there. So that's the canonical divisor for that graph. So then the Riemann-Roch formula, which is due to Baker and Noreen, once again. I should write this down here. Okay. So the Riemann-Roch formula says that if you look at the rank of a divisor and you subtract the rank of the canonical divisor minus that divisor, then this is always a fixed quantity which is simply a function of the number of chips. This is the degree of D minus G plus 1. So this is one of those formulas that just, it takes a while to digest. It's not supposed to be intuitive. It's not supposed to be obvious. I mean, I think a combinatorialist would have a very hard time predicting such a statement. The only reason that they sort of expected such a thing might be true is because there is an analogous statement for Riemann surfaces. Okay. Yeah, so this is the Riemann-Roch formula.
Just one thing.
Yes.
Related to this, what is also basic? Also, what is sourceless? I mean,
Sourceless means that every vertex has at least one incoming edge.
okay.
So a source for me, like if you have, this is classically what someone might call a source, where all of the edges.
Undirected edges.
But I'm also allowing undirected edges. That's still a source for me.
That's still so. Okay.
Yeah. Yeah. Okay, so then I'll take 5 minutes to maybe just say a little bit more about what partial orientations can say about this result. And then I want to talk about maximum and cut for 5 minutes, and then I'll stop. So that's the plan. OK, so here's the description of rank for a chip configuration. I just want to say what's the analogous, or excuse me, what's an equivalent description of rank in terms of partial orientations. So if you have a partial orientation, the rank of the associated divisor is 1 less OK, so the rank is 1 less. This minus 1 is not important. It's essentially the minimum number of directed paths that need to be reversed in this generalized cycle-cocycle reversal system to produce an acyclic partial orientation. So it's kind of a mouthful, but the way you should think about it is you start with some partial orientation and you want to destroy all of the cycles. And you're allowed 4 different types of moves. You're allowed these guys, these 3 moves, but you're also allowed directed path reversals. Okay, so the one thing we're going to keep track of, though, in this game, as we're destroying cycles, is how many directed paths we needed to reverse. So we're not going to keep track of how many times we do these 3 moves. We're only going to keep track of how many times we reverse a path. And every time we do that, we click once. Do some more of these moves, reverse a path, click once, And at the end, the minimum number of directed paths we needed to reverse in this game to get an acyclic orientation is the rank. Well,
you can do whatever operation here as well, in addition.
Yeah, that's fine. But we only care about how many directed paths we needed to reverse. Yeah. So what's a nice corollary of this interpretation? Okay, so what happens if degree of the divisor is g minus 1? Well, you can check. That's like saying you're in the case of a full orientation. So if you have a full orientation, the associated divisor always has degree g minus 1. And you can actually prove the converse, that if you have a divisor which has g minus 1 chips, it's always coming from some orientation after some chip firing moves. So if you have degree of d equals g minus 1, then what does the Riemann-Roch formula says? It says r of d minus r of k minus d equals 0. So these two guys are equal. Well, you can actually see that now immediately from this interpretation of rank. So if you have a divisor d, which say is coming from some orientation O, then r of d sub O equals, and here's the really nice thing, is that if you take k now minus that divisor, that's coming from the opposite orientation.
Complete flip of that.
Just reverse every edge in the orientation. Its associated divisor is k minus d. So all I have to prove is that, I'll use this bar for opposite orientation, is that these two quantities are the same. Well, I claim that from this definition, that's trivial. Why is that trivial? Because every operation you do for this guy just do the mirror operation for the other guy. Okay, so this now becomes a trivial statement, whereas proving such a statement using chip firing is not obvious at all. So that's sort of one example of how this gives some more intuition as to what's going on here. So and then I'll just say one other thing. So the most important result that so there's the original proof, and every proof that's been done so far of this Riemann-Roch for graphs has at least some formal component to it. There's always some formal component. But the most important lemma is the following, which is that if a divisor has degree at most g minus 1, and R of d is negative 1, that just says that you have no winning strategy in this game. So if you have at most g minus 1 chips and you have no winning strategy, then there exists some nu which dominates d, so there's some other guy which dominates d, has exactly g minus 1 chips, and has negative rank still. Okay, so this now, to prove this statement using partial orientations, it turns into a classical result about acyclic orientations, which is the following. This is equivalent to the statement that so given some acyclic partial orientation, you can extend this to acyclic full orientation greedily. So what I'm saying is if you have a partial orientation of a graph, which is acyclic, then you can fill in the orientations of the remaining edges one by one, greedily, without creating cycles. So why is that true? It's kind of a cute proof, so it's worth saying. So this is something that, like, in one form or another you would see in like week 1 or week 2 of your first graph theory course. So suppose you have some unoriented edge that's sitting in your graph. And I claim, so this is a partial orientation. Some part of it is oriented, some part's not, but there are no directed cycles. So I claim that we can either orient it this way or we can orient it the other way without creating a directed cycle. So suppose that that was not true. Suppose that both orientations create a directed cycle. Well, if this orientation creates a directed cycle, then that means that there's some path, some directed path, from, say, u to v in our partial orientation. And the same thing is true for the reverse orientation of this edge. So that means there's some directed path from v to u. And therefore, you have a directed path from u to itself. Therefore, there was already a cycle. So, I mean, it's just very nice that this fundamental lemma from their proof turns out to be like one of these things from week 1 of graph theory. Yeah. So I think that's what I wanted to say. I was going to talk about maximum min cut. I hope I mentioned it in the abstract. I hope nobody showed up just for that reason. But here, I can just say in like 3 words what I was going to say. So as I mentioned, not all chip configurations are coming from orientations, right? Only some of them are. There's a very obvious condition on a necessary condition for when a chip configuration is coming from an orientation, and it turns out that this obviously necessary condition is also sufficient. So this is one of these things that's been rediscovered several times. It originally goes back to Hakimi, who, and then before him for the case of complete graphs, so for tournaments, this was due to Landau. So there is a characterization. And so my observation was that this characterization is actually equivalent to the maximum min cut theorem. So one direction was observed previously by Felsner, and I believe the other direction is new. So I observed that you can use this characterization of which divisors are coming from orientations to prove maximum in cut. So you can go in both directions, so it's equivalent. And then I extended this characterization to partial orientations. And there's various, I give a few different proofs. It's basically you can either go one direction, which is to prove it using submodularity of Euler characteristics, or you can prove it using this game. And that's sort of it. That's what I wanted to say.